Testing. Okay, we'll just wait one more minute for everyone to get seated. What a crowd. Can you hear me? Welcome everyone to the Pennsylvania State University in Erie, Pennsylvania. I am Darren Williams, Professor of Astronomy and Astrophysics, and I would like to welcome you to Eclipse Day at the Behrend College campus, where we are broadcasting live to eclipse viewers across the country. We are seated on the original estate of the Behrend family who donated their land to Penn State 75 years ago to launch an academic experiment that has become Penn State Behrend. The words total solar eclipse have never been uttered here until today. And we are in the final moments, less than 40 minutes from now, before the shadow of the moon first touches the Earth over the Pacific Ocean. And in 3 hours' time, the shadow reaches Erie, and it's not as if we didn't see it coming. Today, the internet tells us when to look, down to the second. But imagine for a moment that there was no internet. No cell phones, no elements of technology anywhere. And suppose in the middle of a normal afternoon, without warning, the sun is slowly gobbled up by the moon. It would be at least startling, if not terrifying, to behold. And so thousands of years ago, this is precisely what happened. These eclipses, they were seen, they were recognized as regular events, but they didn't know when they were coming. They didn't understand what was causing them, and it was deemed a sign of bad future. There was, they were associated with upcoming disease, famine, climate change, battles, wars that they couldn't predict. And so the idea was, well, we need to record exactly when these things happen, but also be able to predict them. And so there was great interest in being able to do that. Stories are told of battles in the Peloponnesian War period, 400 BC, between the Greek city-states, where the eclipses happened during the battles, which caused both warring parties to pause what they were doing and to stop their fighting. And there were momentary truces in between the warring factions. And then hundreds of years later, they finally figured out that eclipses come in cycles, and they wanted to understand the cycles. The Greek scientist Archimedes is supposed to have invented the first analog computer, Archimedes' dial, we call it, which was featured in the latest installment of the Indiana Jones series, Dial of Destiny. How many saw that movie? It was quite entertaining. And that was the first analog computer, but it was designed to predict motions of the moon, phases, as well as eclipses, because they realized that eclipses and their understanding of eclipses meant power. If you could predict when they could happen, then you could motivate people to do things. Does anybody speak cuneiform? So if you recognize cuneiform, maybe you can see the etchings of some of the first eclipses shown here. This tablet is over a few thousand years old. And Columbus, actually, he was a smart explorer, and he either had tables or people who understood the tables, the eclipse tables. And this information actually saved him and his men from starvation. They were stranded in Jamaica. Their fourth voyage, Columbus's fourth voyage to North America, ended in disaster. They were stranded in Jamaica for many months. And in March of that year, the Jamaicans, the natives, decided that they had had enough. And they said, Columbus and your crew, you've overstayed your welcome. We're going to stop feeding you. And they threatened to starve them and to just stop doing their bidding. And Columbus said, oh yeah? Well, what about if you do that, God's anger will be reflected in the shading of the moon in the sky. And Columbus knew that there was going to be an eclipse. So how many have seen a lunar eclipse where the moon turns red? A lot of hands are going up. Me too. I've seen the red moon, and Columbus knew that was going to happen. Nevertheless, the natives were convinced that Columbus had some connection between himself and the deity, and the natives had a change of heart. And they said, okay, we'll feed you. Columbus's men were rescued in July of that year. And everybody knows this gentleman. If I had more hair, I would have pretended to be him today. Einstein may have never seen a total solar eclipse, but he has an eclipse named after him. I call it the Einstein eclipse. In 1919, this was 2 years after Einstein made the prediction that starlight would be deflected by the sun during an eclipse. And I'll just go forward for a moment. What Einstein imagined, and this was a revolution in science, 1917-ish. He predicted on paper, based on mathematics and physics, that starlight from behind the sun would be deflected around the edge of the sun so that it could be seen during a total solar eclipse. Einstein himself never saw the eclipse, but word got out that there was going to be an eclipse visible from the west coast of Africa. And so you see the eclipse path. This was found out by the president of the Royal Astronomical Society of the time, Arthur Eddington, and he said, well, we're going to subsidize, we're going to finance a trip from England down to the island of something or other in the just off the west coast of Africa, and we're going to very carefully see if we can see those stars that Einstein said would be visible. And while Eddington was gone, the story goes, the media found Einstein and said, what if he doesn't see what you predict? And Einstein very casually said, the theory is correct. And lo and behold, he did see, Eddington did, he saw the starlight along the edge of the sun, which was deflected not by degrees, fractions of degrees. It must have been a very difficult thing to measure for the day. But as a result, we call this the Einstein eclipse. Einstein became a household name. He was invited everywhere, North America. This is him in New York City in a ticker tape parade down the streets of New York City. And today we even, 100 years later or more, we refer to Einstein as one of the smartest people that has ever lived because he understood things before everyone else. And so the lunar eclipse that I just mentioned that saved Columbus, most of us have seen lunar eclipses, so you might think, well, they happen more regularly. Not necessarily true. It's just that when a lunar eclipse happens, half the planet can see it. And so if this is the Earth and the moon passes through the Earth's shadow, then the side of the planet facing the moon, everyone can see it. And so chances are in your lifetime, or most people's lifetime, they're going to see lunar eclipses, lots of them. And so I myself have seen many lunar eclipses. That's not the case for solar eclipses, as you'll find out in just a moment. All right, so lunar eclipses happen when the moon is gobbled up by the Earth's shadow. So objects in space, like the Earth, the moon, they cast shadows, and you have to have perfect alignment so that things can pass into shadows. And when the moon passes through the Earth's shadow, you might think, well, it would turn dark, and sometimes it does, but oftentimes it doesn't. It turns red. And the reason why is for the same reason that the sun turns red on the horizon. And you'll see that in just a moment. First, I wanted to show why most people see lunar eclipses rather than solar eclipses. If you're underneath one of these blue shadows, then good luck to you to have clear skies. But also notice that these blue shadows, they only touch a small fraction of the planet. And so most people who live, never are underneath these shadows. Now, I'm a lazy astronomer. When I know about a total solar eclipse, I haven't traveled to one of these blue places, but there are people on Earth who they're determined to see as many solar eclipses as possible. They call them umbraphiles, and they travel everywhere, placing themselves right where the shadow is supposed to be. And there are people alive today who have seen dozens of total solar eclipses. Being a lazy astronomer, I've been waiting my whole life for a shadow to come to me. And lo and behold, in Erie, Pennsylvania on April 8th, 2024, the shadow has come to me. And we'll see what we can see this afternoon. All right, so for the average observer, there's me, and I've lived in 4 places in Pennsylvania and New York over about 50 years. There have been 77 partial or total lunar eclipses available to me, but I've observed only 19 of them because of weather, or because I wasn't paying attention, or because they happened in the middle of the night, which is about 25% of the lunar eclipses available that I've observed. Now, for solar eclipses, they get more press because, again, not as many people are underneath the shadow, and so they get more press, and people find out about it more easily. This one today, the whole planet has found out about this eclipse that is going right through the center of the country. For me, 18 partial solar eclipses available, not a total. I've observed only 7 of them, which is about 40% of the eclipses observed, but they're more memorable because when they do happen, it's a rare event. So most everyone in here has seen at least a lunar and maybe a partial solar, but never a total solar eclipse. After today, there's no excuse. You're all in Erie. You're going to see a total, whether it's behind the clouds or not. We're going to see the effects of the total. Now, I've got you in your seats, and so you are at the mercy of an astronomy instructor. And so I'm going to teach you a little bit about space and scales and stuff. And so you know that the Earth goes around the sun once every year. The moon also goes around the sun once every year. And the two, it's hard to see where you're sitting, but you can see the dot of the moon maybe going around the dot of the Earth. They're really small compared to the sun and space that the Earth and moon are moving through. Anyway, they're 100 million miles from the sun, and they move around together like a binary planet as they go around. So if we zoom in, there's the Earth, obviously. Now what I'd like to do is I'd like to ask, this, by the way, is a good model for the moon. It's the same scale to the Earth as it should be, right? So the moon is smaller than the Earth. But where should I put it, right? So tell me where to put it. Is it there on this scale? Where should I put it? Shout out or raise your hand. Kids in the back, tell me where to stop. Right there? No. Oh, maybe right here? No. No, no, no. No, the true scale, what you do is you imagine 30 of those globes in a line, and maybe 30 is like 30 feet, right? So I'll put it here just because I'm running out of stage, right? And I'll put the moon there. And so this answers your question. You came in with lots of questions. This answers your question. Why don't we get a full, an eclipse moon every month? You know, it seems to me that if you had the moon going around the Earth, and if it was just doing circles like so, that you would see the shadow every month. It's just like, as you'll see in just a moment, the shadows cast by the moons around Jupiter every time it goes around. The reason is as you'll see in just a moment, is that the shadows are really thin and long, and also you never get perfect alignment. But again, back to the size scale, the planet Mercury occasionally goes in front of the sun. The moon is about 3/4 the size of Mercury. And so look at, that's extraordinary, right? Because look at Mercury, the size of Mercury compared to the sun. During a total solar eclipse this afternoon, the moon is going to block out the entire sun. And this makes sense, right? Because the moon is a lot closer, and so just like your thumb, and you should do this during the eclipse, right? So during the eclipse, take your thumb, and you can hold it at arm's length even, and you can block out the whole sun, even though your thumb is infinitely smaller than the moon, or than the moon and the sun. And so small things can block out big things if they're a lot closer. The moon just happens to be a little bit less than 400 times closer than the sun. So they look about the same size in the sky. And as the moon goes around, this is an image from my classes. You know the moon goes through phases, but this is a baffling image. Here's the sun off to the right-hand side, and we see the crescents turning into half moon, and then we go through full. This diagram is misleading. It shows that you should have the moon passing in front of the sun every month. Every new moon you should have an eclipse, and every full moon you should have an eclipse. But that's not the case at all, because that is not to scale at all. All right, so these are the familiar phases of the moon. Once a month we get a full moon. Every 29 and a half days. There will be a quiz after this talk. 29 and a half days, which is almost the length of a month, but not quite. The word month is derived from the word moon, or vice versa. They had a common origin, those two. 27.3 days to get around the planet once, but 29 and a half days between full moons. And while the moon is doing this, the Earth is moving around the sun. And so the Earth carries the moon around the sun like this, and you can think of the orbit of the Earth as like this stage or maybe a body of water. And the moon at certain times splashes up through the body of water the orbit of the Earth and splashes down through like this. And when it does that at new moon or full moon, then we can have an eclipse, right? Well, if you think carefully about it, if you look at this for more than a few seconds, you can see that that happens only 2 times out of the year. So here we have the moon splashing up through or splashing down through the water when it's full, and when it's new, we can have eclipses there. 6 months later, we can have eclipses there. Those are called eclipse seasons. And so you'll notice that nowadays the eclipses are taking place in October. How many saw the one in October or knew about the one in October? Last October, we had an annular eclipse, which is a special kind of solar eclipse. And then 6 months later, here it is today, and we're having a solar eclipse. So 6 months apart, you can have either a lunar eclipse or a solar eclipse. Solar eclipses happen about once, the shadow touches the Earth about once every 2 to 3 years. Lunar eclipses, we just had one a couple weeks ago, but it was in the middle of the night, and I think it wasn't visible from Erie. Right, so the shadows at new moon, because the moon's orbit is tipped ever so slightly, 5 degrees. So this would be flat, but it's tipped by a little bit, 5 degrees. And that means that perfect alignment between the moon, the sun, and the Earth almost never happens. Usually it's the case that during new moon, the shadow misses the Earth, it's above, or the shadow of the Earth misses the moon in the full case. And so we usually don't have the shadows perfectly in line. So there is the long shadow that I just spoke of. So if I put the moon here, you can see how this works, right? So if the sun is over there today, that's for what I've done here on the stage. The sun is infinitely far that way, and that shadow would be really long and thin, and it would just barely touch the surface of the Earth. In about 15 minutes, that shadow touches the Earth for the first time, right? So all the people, the tens of millions of people in North America celebrating with their wine and cheese and bouncy houses and all that they're doing, everybody's waiting for that shadow to come to them. And hopefully, again, the clouds will cooperate. Maybe for us, we'll see. All right, so the moon, not only is the moon's orbit tipped by a little bit, if it weren't tipped, you might think, well, it's not a big deal, it's 5 degrees. If it weren't tipped, then every half month we would get an eclipse, either a solar eclipse at new moon or a lunar eclipse at full moon, and then the eclipses would be regular, and I wouldn't be standing up in front of you and getting all your attention. But because of that 5 degrees, it's an infrequent thing. And it almost never happens for any one location on the Earth. So let me go back. I want to show you that not only is the moon's orbit tipped, but also it's not circular, not exactly circular. So sometimes it looks big in the sky. We call that a supermoon. How many have heard of the word super? I love it when the news comes out. Tonight is the supermoon. Go out and see it. You should still be able to cover it up with your thumb. All right, try that the next time. It's easy to do, and it does look bigger and brighter. It does, to me even, but it's not much bigger than the small moon, which is right here when it's furthest away from the Earth. But that difference between that size and this size means everything, as you'll see in just a moment. Right? So sometimes it's too far away from the Earth and it can't block out the whole sun. We call this an annular eclipse. Let me go back again. There we go. We call this an annular eclipse because it's an annulus of light. The edge of the sun is not blocked out. This is what happened in North America. Starting in Oregon, it passed through the center of the country. The moon was right in front of the center of the sun for everyone from Oregon and down to Texas. This happened in October, 6 months ago. So now 6 months later, now the moon is actually closer to us, and it can block out the whole sun. Now, how many people live in Erie? How many Erieites? So maybe not as many as we would expect. But people in Erie might remember this eclipse, May 10th, 1994. The path of annularity passed right through the center of the country. It looks very similar to what's happening today. Right through the center of the country, right through Erie, Cleveland, Erie, and we would have had a total solar eclipse. This was 30 years ago, exactly 30 years ago. We would have had a total solar eclipse, but the moon was a little bit further away from the Earth, passing down through the plane of the Earth's orbit this way. But it was the same path that the shadow was taking through North America. Now you might say that the astute mathematicians and astronomers in the audience might say, well, that was 30 years ago. There must be a cycle, a 30-year cycle, and there is. And it's called the INEX, I-N-E-X, the INEX eclipse cycle, right? And so there's a 30-year period. What in the world is the INEX cycle and where did it come from? Google it later. That's not the one I want to focus on. The 30-year period is there, it's real. It has to do with changes, slight changes in the Earth's orbit and the moon's orbit caused by the pull of the other planets over time. But there's another cycle. It's called the Saros cycle. If you're curious about eclipses and the frequency and how often they happen on the Earth and when the next one is going to happen, then you have to know about the Saros cycle. The word Saros is the Greek version of the word SAR, which if you Google it, it's disappointing. The word SAR stands for the number 3600, which is the number of seconds in an hour, the number of arc seconds in a degree. So we use 3600 all the time, but it has nothing to do with eclipses. The first person to utilize the word Saros and apply them to eclipses was Edmund Halley. Oh my goodness, all this history. He's given me all this history. I've heard these names. Edmund Halley, who was that? Edmund Halley, 350 years ago, he was interested in everything. And especially eclipses and how they worked and stuff. So he was one of the first to use the word Saros, which was derived from words passed down thousands of years earlier. Saros, 1660s, 1670s. And we call the current model of eclipse keeping, we use the word Saros to represent the cycles. The 18-year Saros cycle is alive and well and commonly understood and known. These are animations of the May 94 eclipse. Here's the shadow passing in front of the Earth. This is April 8th, and it's very similar. They travel at about the same rate, 30 years apart. We would have had a total solar eclipse, but the moon was too far away. But they're not exactly the same, are they? So they get us thinking about cycles, but this is not an exact replica of what happened in 94. Okay, so we have the sun 93 million miles away. Here's the Earth, and the moon's orbit. It's not exactly a circle, and the moon is really far. It's 5 degrees tipped and stuff like that. But in addition, it's precessing like a top. And I'll do this in front of you. You've seen this before, so that's not very impressive. But you can recognize that precession on the stage here. If I spin this wheel, now the moon's orbit is not solid like that, right? The moon is going around the Earth. If you took a time lapse, if you took a photograph every day, then the moon would fill in its orbit. So imagine the moon is filling in its orbit, and now it's a continuous circle of mass. And now that mass is rotating once a month, like this bicycle wheel. If I were to do this in space and just let it go, it would just stay pointed in one direction, ignoring the pull of the sun and the Earth. But in here, the elephant in the room is the pull of the Earth. And so it doesn't stay in one direction. It precesses like a top. And if this were the orbit of the moon, it would do one cycle every 18 12.5 years, roughly. And so who cares? Why am I talking about this? Because those eclipse seasons with perfect alignment for eclipses, they move around the calendar. So in 2017, how many saw the solar eclipse in 2017? When did it take place? What month? August, right? So the eclipse seasons in 2017 were August, and what's 6 months later? February, right? So August and February. And now the seasons have drifted. They've drifted around the calendar so that now it's October and April. And then next year they might have drifted a little bit more so that it's September and March. Right? So every 6 months we have the chance for eclipses, and they drift around. Why? Because again, the orbit is precessing like a top. Why? You have to know some physics, right? And the elephant in the room for the moon in orbit around the Earth, the sun is also tugging on the moon. You might think that the Earth is the only thing tugging on the moon. It's the sun which causes this precession. In addition to the shape of the Earth not being perfectly spherical. Anyway, all that physics, we'll put that behind for a moment. What does this mean for us? It means that eclipses come in cycles, and these cycles we refer to as Saros cycles. The modern record-keeping and tabulation of Saros cycles was actually established recently in the 1950s. And so if you Google it, and you'll get into a lot of math and cycles, and it's not impossible to understand, but it is complicated. At any one time, there are dozens of Saros cycles going on. Let me just show you the pattern. So this is the path for July 2009. And then 18 years later, it's a third of a rotation of the Earth over here. And then 18 years later. But also, so not only longitude is changing in these cycles, but latitude. 54 years, 3 times 18. 54 years later, it occurs with the same geometry, the same longitude, but down here like this. It takes thousands of years to go through a complete Saros cycle, and here it is, I think. Yeah, thousands of years to go through the whole business. The cycles start with eclipses taking place near the North Pole. They go through the mid-latitudes like we're experiencing now, and then they end up close to the South Pole. And then we start a new cycle with new geometry, new distances between the Earth and the Moon when the cycle starts, new orientations of the new geometry, new orientations of the orbit of the Moon at the start of the cycle, new rotation information, latitude and longitude information for each cycle. Okay, now the Earth and the Moon aren't the only ones in the solar system that produce eclipses. This is a shadow cast by the moon Io in front of Jupiter. There are lots of moons of Jupiter. 4 of them are the big ones. They're called the Galilean moons, and they cast big shadows, well-defined shadows. For the Earth-Moon system, the shadows are smaller, about 100 miles wide, right? So, and 100 miles compared to the size of the Earth, this globe, it's even smaller than that dot that you can see with the laser dot on the globe that I'm showing you there. So this is actually a really small umbral shadow, which just happens to be passing directly over Erie today. And here's an animation of what happened in 2017. The shadow cast by the moon. The camera in this case, and it wasn't an actual camera, this is an animation produced by NASA. The camera is following the moon as it flies around the Earth. The Earth is rotating underneath, so there's motion all over the place, and it's kind of confusing. The moon is moving thousands of miles an hour around the Earth, while the Earth is rotating underneath, which all of that affects the rate at which the shadow flies over the Earth. By the way, we're within minutes of the shadow first touching the Earth. Hooray! Yeah. Okay, so it's exciting to think about. And that shadow, you can see just in a few hours. If you remember, it was just an hour and a half to get across North America back in 2017. And like I said, the Earth is rotating really fast underneath. Sorry, let's go back. 1,000 miles an hour at the equator. In this room, it's hard to believe, but we're all going at around 600 miles an hour around the center of the planet. The air molecules, your seats, me, you, everybody is going the same speed, so we don't feel it, but we're all rotating really fast around the center of the planet, which affects the rate at which the shadow passes, the shadow of the moon passes overhead. And so here is the path, and you can find these pictures on the net. The shadow first touches, like right now, perfect timing, I timed it out. Right now, the shadow first touches the planet 1,000 miles south of Hawaii in the Pacific Ocean. And that's like right now. So you might be saying, Mom, Dad, when is the eclipse you keep talking about? It's 3:15 today. 3:15 today, that's up here, right? So that's in a few hours, and it's going to take a few hours for the shadow to reach us up that path. Now, for those of you who want to extend the time it takes the shadow to go overhead, you might think, well, maybe I could travel with the shadow at the same rate. No, you can't, except in a rocket ship. It really is traveling at rocket velocity across the face of the Earth. Here's the moon, 2,000 miles an hour. Here's the moon's shadow as it flies through space. The rotating Earth underneath. Here's the projection of the shadow on the surface of the Earth. And notice that in mid-flight, this is Mexico. This is Indianapolis, maybe Erie, and this is near Nova Scotia or the North Atlantic. Notice the shadow gets elongated as it goes around closer to the edge of the planet. And so if we look at this, you can see this is just about to touch Mexico, and you can see the time, Mountain Standard Time, and the shadow velocity, 1,500 miles an hour. Now, if we move ahead, now we're in Texas, and the shadow velocity, 1,600 miles an hour, 4 minutes and 22 seconds for it to fly over, and it's kind of a circle. If we continue on, this is Indiana, 1,977 miles an hour, a little bit shorter, and this is at 3:07 p.m. Eastern Daylight Time. This is us. The shadow is passing overhead, and Erie is right there. The center of the shadow is actually about 7 miles off the coast of Erie and into Lake Erie. And the people who are on Presque Isle today, they're on Presque Isle because it's beautiful on Presque Isle, but also it's a few seconds longer eclipse on Presque Isle than it is here at Behrend College. And if we advance forward to the end, this is Ontario, New York, and you can see the velocity of the shadow is getting higher because it's getting elongated. You can see it getting elongated, and it's traveling faster and faster as it gets close to the edge of the planet. And here is the most elongated shadow. This is Newfoundland, Labrador, 4,000 miles an hour. Technically, that velocity goes to infinity, but it's not that the moon is increasing its speed as it goes around. It's that the projection of the shadow as it touches the Earth, it gets faster and faster, and then right at the edge of the planet, it blinks out quickly at an infinite relative velocity. Okay, so this is the shadow for today. And again, you might think, well, if I board a plane in Texas, how many have heard of this? You can buy plane tickets in Texas today. In fact, they're probably on the tarmac now, right? And what they want to do is they want to fly from Texas to Detroit or thereabouts along the shadow to lengthen their eclipse experience. But again, how fast do you need to travel? How fast is that shadow going to go from one part of North America to another? It's thousands of miles an hour, right? And no passenger airplane travels 1,000 miles an hour. The fastest ones are maybe a third of that velocity. And this is your experience. Maybe you'd be on your knees, or you'd be in the regular seats, just looking out. And this is what you would see. During a total solar eclipse in a few hours, we'll see how dark it gets. It's not dark as midnight, but it will look significantly dark. In fact, the street lights might come on. The Behrend lights, I think, have been programmed to not come on during the eclipse today to maximize our viewing experience. But maybe Peach Street or the highway lights, maybe they will come on if they're on sensors. And this is the darkness of the sky, and you see the eclipsed sun. Most of the energy of the sun is coming from the circle called the photosphere, and that's going to be blocked out, leaving behind the corona, which is the atmosphere of the sun. Right? So during the eclipse, we're all told to wear our glasses, and there's great confusion involving these glasses. People think that one, you can only use the glasses during an eclipse. You can use these glasses whenever you want. I've been using the glasses all the time when I'm outside looking at this. So here's my advice. Anytime you're tempted to look at the sun for more than a few seconds, you're not going to instantly blind yourself if you look out. You know this from experience. And so there's no difference today because it's eclipse day. You're not going to blind yourself just by going outside. There's a lot of misconception about this. So your assignment is to spread the word to everyone. You can use your eclipse glasses every day of the year. It's fine. And even today, if you're not looking at the sun, you don't need the eclipse glasses, right? But if you are looking at the sun, and if you have children who are tempted to look at the sun, then you want to look with your glasses on. So starting at around 2 o'clock in the afternoon today, the moon will start to eat away at the edge of the sun. And then by 3, it'll be almost time. The hallelujah moment happens at about 3, for us locally, at about 3:16. All right, so here's an animation, right? So during the hallelujah moment, it's not a moment, it's 3 minutes and 40 seconds for us in Erie. The glasses go off, but then when that moment is over, then the glasses go back on. If you forget to take your glasses off, somebody's got to remind you. So remind each other, take your glasses off during the 3 minutes and 40 seconds, because then you'll be able to actually see the corona of the sun, maybe a solar flare, maybe planets and stars and stuff. And then the moon will repeat, but on the other side of the sun. It'll leave the sun over a few hours. By 4:30 today, the whole thing is done for Erie. All right, now, close to the middle, you might see bright flickerings and flashings of light along the edges. What that is, that's sunlight that's passing through. It's tunneling through the edge of the moon, valleys and mountains of the moon. And so the last coverings of the moon over the sun might be accompanied by these flickerings and flashings, first observed by Francis Bailey, again, and there's going to be a quiz afterward. Francis Bailey, 1838, 6, in which he observed these, what he called, well, he might not have even called them, he wrote about them. We call them Bailey's beads today, right? So if you're out there and you see these flickerings, some people call them the diamond ring effect, or a string of pearls sometimes, or Bailey's beads, and this is what they mean by them. Let me show you some more images of them. So we might see, I can't guarantee it, it depends on the geometry of everything, but you might see close to totality these last flickerings of sun along the edge of the moon. And now everyone, including myself, is going to be looking carefully at what's called the corona. This is This is the atmosphere of the sun. It's about 1 million degrees, which seems strange because the surface of the sun, the part that we can see where all the light comes from, 5,000 degrees, 10,000 Fahrenheit, but 5,000 roughly Celsius and Kelvin. But in the atmosphere, it's more like millions of degrees. Why? Why is it hotter as you move away from the sun? It's because of the sun's magnetic field, which is really strong. It's thousands of times, hundreds to thousands of times stronger than the field in this room, maybe even stronger. And in the corona, the sun is ejecting billions of tons of matter into space at millions of miles per hour, mainly protons and electrons, which we can't see, but these things fluoresce and they give off some light, which can only be seen when the main light source of the sun, the photosphere, is blocked out. So we call it the corona. The structure of the corona depends on the health and phase that the sun is in. The sun goes through cycles itself, and it turns out that the sun is going through a behavioral cycle right now, which is maximum for solar activity in the corona. And so we're all excited, the astronomers anyway, are excited to look and see if the corona is well behaved or whether it's misbehaving, so that there's stuff being thrown at high velocity, solar flares, we call them prominences, sometimes we call them. Again, millions of miles per hour, this stuff is being thrown around by the sun's magnetic field. Sometimes we get an explosion, sometimes referred to as a coronal mass ejection. Again, billions of tons of material all at once, millions of miles per hour into space. Occasionally, that ejection goes in the direction of the Earth. So if you can imagine, there's our fragile Earth over there, and all this stuff, millions of miles per hour, protons and electrons coming at the Earth. And about here, protons and electrons, charges, they start to sense something. And they start to feel the magnetic field of the Earth. And they start to spiral like this. And they get deflected by the Earth's magnetic field. Fortunately, we have this field. It's like in Star Wars, the force field. We're opening the magnetic field around the Death Star, right? So there's this magnetic shield around the Earth. And around this distance, those protons and electrons, they start to get deflected. They feel the Earth's magnetic field, and they start spiraling like this, and they impact the upper atmosphere of the Earth near the magnetic pole, which is near the North Pole, not exactly the same thing, but in the upper latitudes, the high latitudes of the Earth, and they splash down in, and they excite the molecules in the Earth's atmosphere. They cause them to fluoresce. If I could have the slides back again. No, let's go back. One. Okay, right there. So occasionally they cause an auroral display. How many have seen the northern lights? Right? And the reason why there aren't more hands is because at our latitudes like us, we hardly ever see the atmosphere responding in this way because those splashes of protons and electrons, they take place more northerly latitudes, Scandinavia, Alaska, northern Canada, Greenland, etc. But in 2003, I was teaching a lab here on the Behrend campus, and a student of mine had a camera, and the whole sky turned red and green, exciting the molecules of nitrogen and oxygen in the atmosphere. And we didn't know it was coming at this low latitude. Sometimes it happens, maybe once every 20 years or so, it happens. And this was a beautiful photograph. You can see there's observatories down here. The Mahassel Observatory is shown here on the horizon, and the whole sky for a half hour fluoresced red and green. Occasionally in Erie we get treated to a show like this, but it's very rare, and it's unpredictable. It depends on the last solar explosion and whether the explosion sends material in the direction of the Earth or not. Speaking of eclipse seasons, in October, we had the path of annularity there, which went from Oregon into Texas. Now we have totality. This path, goes where it goes up through Erie. And annularity, this is what an annular eclipse looks like, in which the moon is too far from the Earth to block out the whole thing. So we see the dark part of the dark side of the moon covering up most of the sun, but not everything. This is what happened in May of '94 in Erie. And so these are the two paths, and if we zoom in, I think the next one, right here. This is Carbondale, Illinois. In August of 2017, the path went right through Carbondale. Today, in an hour or so, Carbondale will see the second total solar eclipse. So if you ever want to go to Carbondale, I'm sure they're going to have a museum there someday. It's a very strange, coincidental situation for two total solar eclipses, one location on the planet Earth in 7 years. Carbondale, Illinois. And near San Antonio is where these two paths cross, so that's also very rare. But it wasn't total in last October. So this is the moon's shadow in a few hours. There's Cleveland, and there's Erie. Hopefully the shadow of the cloud will move at the same rate, so the moon shadow will push our clouds away, and we'll have clearness. Everybody in North America is treated to this experience. So if you're along the main band here, you can see totality for a few minutes. But even in Florida, 50% of the sun will be covered. In California, it depends, 50 to 80%, depending on what part of California. And then these are the Verbo reservations, right, just a few days ago. And you can see the trend. You don't have to have an astronomer point it out to you. You can see where people want to go. Now, if it is perfectly clear here, or wherever it is clear, during totality, you should be able to see stars and planets. And so there's the sun and the moon. It's hard to see from where you're sitting, so I'll point these out. Right, so you'll see Mars and Venus and Saturn off to the right. You have access to the entire solar system. There's Saturn and Mars. There's Venus, one of the brightest stars in the sky. And then to the left, there's Jupiter, again, one of the brightest star-like things in the sky. Right around Jupiter, right near Jupiter, will be a comet. I think I'm going to show that to you in just a moment. But these are the wintertime stars, which are really exceptionally bright. There's Orion, the hunter. So if it is clear and if we get a good sky today, we should see some bright stars, Orion, Gemini, Taurus, and so on. Let's move forward. All right, so the comet, what is it? It's called Comet Pons-Brooks, named after the astronomers who discovered it a few years ago. And it has a tail. And I've been told, I haven't seen it myself, but I'm told that you can see it with binoculars, and maybe during the eclipse. Here's the sun, there's Mercury, there's Jupiter, and here's the direction of the comet. So if you have binoculars today, for the 3 minutes and 40 seconds, take a look and see if you can see that comet, Pons-Brooks. It's in a Halley-like orbit. Again, this is hard to see from where you're sitting. It goes around the sun once every 71 years, and we'll see what we can see today. This is through a big telescope. You can actually see, it's got horns, so they call it the Devil's Comet, because it's got these strange horns to it. It's a lump of ice and rock, and it's evaporating as it gets close to the sun and spitting out its material into space in these strange directions, and so they look like horns. The other thing to look for during the eclipse, if it is clear skies and close to totality, you'll see strange shadows on the ground. This is where the sunlight tunnels its way through leaves in the trees, maybe needles in pine leaves. You'll be able to see strange shadows cast all over the place. If you haven't seen these before, it's quite extraordinary. So there's fun looking up, but there's also fun looking down, interesting things to see looking down. Now, during the normal day, the sunlight also tunnels its way through the tree leaves, but there's too much diffuse light coming from all directions. And you do see the images of the sun projected on the ground, but they're more fuzzy. They're all diffusely made, and we hardly ever pay attention to this stuff. But during a solar eclipse, it is evident that something strange is going on. All right, so the next, you've been told, if you missed today for some reason, the next big one is in 20 years. This is in August. The eclipse seasons will have drifted by then. 20 years, 2045 is where the shadow, and it goes right from, again, northern the Pacific, near, there's Oregon, and then it goes right through the center of the country into Florida in 20 years. So mark your calendars, go online and start reserving your hotels. Get your eclipse glasses. You know, this is 2045, August. And again, this is the path. It's a little bit fatter than today, so the eclipse will be a little bit longer. If your great-great-great-great-grandchildren are alive and paying attention, they will see this one in 2144. It starts in Alaska, goes down through the Great Lakes, right through Erie, and that'll be the next. Maybe at the Behrend College campus, there will be a talk. My great-great-great-great-granddaughter will be giving that talk on this stage a long time from now. So to conclude, the power of eclipses is that they awaken a childlike sense of wonderment and curiosity in people of all ages, including myself. So on this ordinary spring day in April, we'll pause for a moment as if faintly aware of an extraordinary and yet tranquil natural event. We'll stop the car, pull over on a busy street, or leave our tablets, keyboards, and screens. And we'll step outside, warm or cold, dry or wet, sun or clouds, as if compelled by an invisible hand to lift our heads and look up. All of us transfixed for a moment by a rare and marvelous spectacle of cosmic proportion as the shadow of the moon flies overhead. We are hereby given a backstage pass to the intricate and wondrous machinery of nature. And all of us will in this moment become, according to the astronomer Carl Sagan, a way for the cosmos to know itself. And we might say, good night, sun, hidden by the moon. Good night, light in the afternoon. Stars and planets appearing there, joining the corona and the solar flare. Everyone staring at the cold, dark sky. Amazing to all, the sun is shy. Everyone staring into the cold, dark air. Amazement to all, everywhere. Thank you very much.
You never really want to come on after that. But invited guests, students, alumni, teachers, community members. I'm Dr. Marty Kozlek, Director of the School of Science here at Behrend. It's truly my pleasure to welcome you out to Behrend on this special day. Please, let's thank Dr. Williams again for really outstanding, entertaining talk. We've got a variety of events and things going on today around campus. For our student guests, of which there are like 1,000 of them in the back of this auditorium, K through 12 students spending the day with us. A lot of things going on. For those of you participating in the rocket contest, which we'll have going on, you can join Behrend faculty and staff on the softball field, which is going to be down in this direction across the parking lots. Those wishing to have lunch and purchase lunch in the Reed Union Building, which is up across the parking lot in this direction at Bruno's. As we approach, as Darren said, approach 202, which is going to be the beginning of the eclipse here in Erie. You've got a number of places you can view it from. If you're looking for more of a quiet, laid-back place to view it, Behrend Fields. Across here and in the corner, there's signs towards Behrend Fields, and we suggest going out there. Or if you want a livelier environment, it includes concessions, a DJ, telescopes for viewing. Head over to Behrend Soccer Fields, which are off in that direction. We've got lots of volunteers with yellow necklaces around them or yellow vests who can direct you in wherever you need to go. So no matter how you choose to view the eclipse today, whether you're coming from near or far, let me thank you again for choosing to spend the day here at Behrend with us, really for this once-in-a-lifetime event. So I hope you have a fabulous day. Welcome, and thank you all.